Okay, so one of the important properties of an interface is that at an interface you can get adsorption, or also sometimes called segregation. So to understand this, let's consider a phase-separated liquid system. Comprised of a solvent, which will be species 1, and a solute, which will be species 2. Okay. So then we know that we can write down both our equation for the differential of the energy. So we have du is equal to T ds minus P dV plus sum over all species mu I dNi plus gamma dA. And we can write down our full equation, right? U is equal to Ts minus PV plus sum over mu I Ni plus gamma A. And we know whenever we have two equations like this, one that's a differential and one that's a relationship between the undifferentiated quantities, that we have a Gibbs-Duhem relationship that relates those. So Gibbs-Duhem then tells us that for this to be true, for us not to have to worry about the SDT term, the VDP term, etc., SDT minus VDP plus sum over I Ni d mu I plus A d gamma must be equal to 0. Okay. And that has to hold both for the pure phases, right? So I can write down S alpha dt minus V alpha dP plus sum over I Ni alpha d mu I. But here, of course, in the pure phase, there's no interface, so that has to equal 0, right? And also for the B phase, and also for the system as a whole, right? So if we subtract both of these from this for the entire system, we get a Gibbs-Duhem relation in terms of the excess quantities. Okay. By subtracting the pure Gibbs-Duhem equations from the system Gibbs-Duhem equation, we get that the excess entropy, dt, minus the excess volume, dP, plus sum over I, the excess numbers of species, d mu I, plus A d gamma has to equal 0, according to Gibbs-Duhem. And now we're going to use the fact that we chose to put the interface such that Vex is 0 and N1Ex is 0. So what we end up getting at the end of the day is that d gamma is equal to minus Sex dt. The V drops out, and then we just have minus N, and N1 is 0, so we just have N2 Ex over A d mu 2. So this is known as the Gibbs adsorption equation. And it's interesting because this quantity over here N2 excess over A is the concentration of the solute in the interface. Right? It gives the number per unit area of species 2 in the interface region. And so by this equation, we can see that gamma 2, or minus gamma 2, is equal to, by definition, the derivative of gamma, the partial of gamma, with respect to mu 2 at constant temperature. Now, if we further assume, so if we also assume that mu 2 is dilute, or species 2 is dilute, then we can write down an expression for mu 2. We can say mu 2 is equal to mu 2 star, pure mu 2 plus RT natural log of C2, the concentration of 2. And in that limit, then we can say that, okay, we can write down that d gamma dC2 is equal to d gamma d mu 2 times d mu 2 dC2. So that would be minus gamma 2 times d mu 2 dC2 would be RT over C2. Right? So we can relate the derivative of the free energy, of the surface energy with respect to the concentration of the solute to the concentration of the solute in the interface. So there are two possibilities here. If we think about the concentration of our solute as a function of our surface energy, it's possible that, so that you have some concentration, let's say, in the extremely dilute limit, but then you could have, or, well, is the concentration, let's call this 0, is concentration of 2, right. So we're looking at how the surface energy changes as we change the concentration of 2. So there's some surface energy when you have no solute in the interface. So it's possible that you have case 1, we'll call it, where adding solute to the interface reduces, adding solute reduces surface energy. Or we could have case 2, where adding the solute increases surface energy. And what this tells us is that in case 1, right, we know C2 is greater than 0, right? We know d gamma dC2 in case 1 is negative, is less than 0, right? So as a consequence, gamma 2, which is equal to minus C2 over RT d gamma dC2, right? This is greater than 0, this is greater than 0, this is all positive, this is negative. That has to be, this has to be greater than 0 because this is negative and we have a negative sign. And so there will be an excess of concentration, excess solute in the interface. On the other hand, for case 2, right, we know C2 is greater than 0 and d gamma dC2 is greater than 0, right, because the slope here is positive, and that tells us that gamma 2 must be less than 0 by the same argument, so we have solute is expelled from the interface, right? So we have these two cases that are given to us by the Gibbs adsorption equation, where depending on whether the solute would strengthen the interfaces or weaken the interfaces, it will either be drawn into the interfaces or expelled from the interfaces of the material.